Hello, welcome to our demonstration of some of the recent projects we've been doing in our lab. Our lab designs and makes materials, software, and hardware for 3D printing clay and other paste-like materials. This is a common 3D printer that we use in our lab, and it is made for clay, which is a material we use often. It's been seen in some of these smaller vessels, as well as this bigger sculpture, which was printed using a different clay 3D printer. Our work with clay and these printers, though, made us curious of what other materials could be used in this printer.
So some of the other materials that we use with this printer include Play-Doh, which is a corn and wheat flour based biomaterial that is easily recyclable and compostable, as you can see by this sample that's being nice and moldy. Along the same lines as our Play-Doh is an eggshell based biomaterial. It is also easily recyclable and highly compostable, and we really envision using it for creating temporary biodegradable animal shelters. Beyond our biomaterials, we use a clay-dough material, which is a mixture of clay and Play-Doh. So as we fire it in a kiln, the biomaterial dough burns away completely, causing this very dramatic shrinking behavior to occur. So these three samples here were actually all the same vessel printed, and then they shrunk into different forms depending on the ratios of clay to Play-Doh we used in the print. We also work a lot with bronze clay, which is made out of metal clay that then that sinters completely during the firing process, creating solid bronze pieces like this cup, our Stanford bunny, and some other items like wrenches and jewelry. One of the last materials we work with is this glass paste. Similar to the bronze clay, it's made out of a glass powder that sinters completely when we fire it in our kiln.
So all of these materials have different material properties and behave differently when 3D printed. They all took lots of different iterations and trial and error when coming up with the recipes, and they just have different physical properties. For example, the metal and glass both have non-linear rheology, which means that when we use them in the 3D printer, they continue to extrude even when we turn the extruder off. So that presents a problem when 3D printing because you want it to stop when you tell it to stop. But what that means is that our lab also, in conjunction with these materials, creates and builds software to accommodate them. So one of the software that we have developed is a slicing software that handles this nonlinear rheology. And it does that by minimizing travel paths, by using format spiraling, as well as a non-traditional linear or vertical segmentation of forms to eliminate those travel paths and be able to print nice and smooth forms like that Stanford bunny. We also use our deep understanding and knowledge of clay to come up with another slicer called Weave Slicer. And that slicer is specifically meant for clay 3D printing, and it expands the types of geometry that are printable with clay 3D printing. So it does that by maintaining a uniform wall thickness throughout the print, and it does that by printing with a sinusoidal toolpath where the amplitude is adaptable based on the overhang angle of the form.
Beyond the software, we also develop new hardware that can be used in conjunction with our clay 3D printers to support some of these materials. So one piece of hardware is this heater and fan that fits around the extruder of our printer. So it dries the material as it is being printed, which leads to more structurally stable prints. By creating materials, software, and hardware together, we hope to highlight this entangled development process in digital fabrication.